I'm Chicken. This is lab 4 for physics 2. So the purpose of the lab was to observe and take data from a magnet falling through an aluminum tube and use this data to apply Faraday's law. Then the fundamental principles that we need to know for this are obviously Faraday's law, which is basically says that the magnetic field caused by the falling magnet will induce a current in the aluminum tube. We also need to know this law, which gives us the equations that yield magnetic field due to a segment of current. And then we need to know Ohm's law, which relates voltage, current, and resistance through V equals IR. And then we need to know magnetic force in a loop and flux due to a dipole. The models of assumptions. So our models that the magnet is a dipole with the north and south end. The assumptions are that gravity and the magnetic force are the only forces acting on the magnet as it falls. And we're assuming that air resistance is negligible, so we can ignore it. So the experiment was the aluminum tube was held perpendicular to the floor and the magnet was dropped through it. And a recording was taken of this, and the times that the magnet entered and exited the tube were found by scrubbing through the video and taken down. And then this data was used to find the average time it took to fall through the tube, and the average velocity through the tube was found. And then this process was repeated 5 times for the different runs. So this is a setup of the experiment. It's my brother holding the tube. He's about to drop the tube in this end, come out that end, take those 2 times. That's it. So our measurements and data, the measurements for the tube is that the length was 30.5 centimeters. The width was 3.5 centimeters, which means the radius was 1.75 centimeters. The magnet had a mass of 0.025 kilograms. Run 1, these are the times for all the runs, so that means that the average is 1.038 seconds through the tube. So this is the computational model of the situation. These are the measurements on the tube that I just showed you in the last slide. This whole section just sets up the tube. This section sets up the magnet. These are the measurements from the magnet that we just showed. These are the initial conditions since it was dropped from rest at time 0. That is a velocity of 0, obviously. And then this creates the magnetic field of the bar magnet here. And then this creates the magnetic flux due to the bar magnet through the tube, these equations. And then this creates the motion of the magnet falling through the tube, so that's like what you actually see in the video when you hit run. And this calculates magnetic force on the magnet. This calculates the F net, which is when you add gravity and the magnetic force, since we're assuming those are the only 2 forces acting. These are velocity and position update for the magnet. That again just helps the magnet to move through the tube in the model. And then this creates the position versus time graph, which you'll see soon. So as you can see, this is it falling through the tube. Obviously this is the tube, this is the magnet with its north and south end, and then this just shows the progression as it falls. This is the velocity and time graph that it yielded. So what if the resistivity of the conductor was reduced as close to 0 as possible? How would the dynamics of the falling magnet change? So since R and I are inversely related according to the equation, I equals V over R, which is Ohm's law. If the resistivity was reduced to near 0, then the current would become very large, which would cause the magnet to fall slower through the tube. And then the other what if question, what if holes or slots were cut into the tube? How would this affect the rings of current in your model? So if holes or slots were cut into the tube, this would mean less rings of current in the tube, which would obviously cause a decrease in the overall current. So therefore the magnet would fall faster through the tube, so our average time would be